This video introduces the paper, Adaptive Flip Graph Algorithm for Matrix Multiplication by Yamato, Arai, Yuma, Ichikawa, and Koji, Hukushima. The paper presents a novel approach to matrix multiplication, a critical operation in computational processes. The authors propose the adaptive flip graph algorithm, which enhances the efficiency of matrix multiplication, especially for large matrices. This innovation addresses the limitations of the original flip graph algorithm by introducing adaptive strategies for overcoming challenges in exploration and search efficiency. Matrix multiplication, fundamental in computational processes, has seen various optimization efforts. Traditional methods, including Strawson's algorithm, have focused on reducing multiplications in matrix operations. A notable advancement in this field is the introduction of reinforcement learning with alpha tensor. The flip graph method, another recent development, employs a graph representation with respect to matrix multiplications and utilizes its topology to optimize the computation. This paper builds on these foundations, aiming to address inefficiencies in these existing methods, particularly in handling larger matrices and optimizing the search process within the flip graph framework. The flip graph algorithm, while innovative, faces practical limitations, particularly in dealing with large matrices. The paper identifies two main challenges: non-reduction states, which hinder further exploration, and inefficient searches in large matrices. These limitations become more pronounced as matrix sizes increase, necessitating an improved approach to optimize the process. In response to the identified challenges, the authors introduce the adaptive flip graph algorithm. This innovative approach adapts the search process dynamically, addressing the non-reduction states and inefficiency in large matrices. By introducing flexibility and constraints in the algorithm, the adaptive flip graph method offers a more efficient and effective approach to optimizing matrix multiplication. The adaptive flip graph algorithm incorporates two key strategies: the plus transition and edge constraints. The plus transition allows for rank increase, enabling escape from non-reduction states, while edge constraints strategically limit the search space, enhancing efficiency. These adaptive strategies enable the algorithm to navigate the flip graph more effectively, especially for larger matrix multiplications. The authors conducted extensive tests comparing their algorithm with alpha tensor, a notable method in matrix multiplication optimization. For the multiplication of a 4x5 matrix by a 5x5 matrix, both the traditional flip graph method and alpha tensor had previously achieved a multiplication count of 76. However, the adaptive flip graph algorithm marked a significant advancement by reducing this count from 76 to 73, thereby outperforming both the traditional flip graph method and alpha tensor. While these matrices might seem small, optimizing the multiplication of such matrices is crucial. This is because large matrix multiplications can be broken down into smaller ones. Therefore, improving the efficiency of smaller matrices has a dramatic impact on the efficiency of large-scale matrix operations. Similarly, for two 5x5 matrices, the reduction was from 95 to 94 multiplications, again surpassing the existing benchmarks. Historically, for two 5x5 matrices, the flip graph initially discovered a solution requiring 97 multiplications. Alpha tensor then improved this to 96. Subsequently, the flip graph algorithm used alpha tensor's result as a starting condition and found a way to reduce the count to 95. In this research, the adaptive flip graph algorithm further reduced the count to 94 multiplications, underscoring a significant advancement in the field. In conclusion, This paper marks a significant step in optimizing matrix multiplication. The adaptive flip graph algorithm tackles major issues in current techniques, proving to be more efficient and effective. The authors aim to extend these strategies to larger matrices and explore further innovative approaches, continuing the advancement in computational efficiency and matrix multiplication optimization.